Hello everyone, welcome to Programming Knowledge. In this video, we will discuss what is machine learning and what exactly is scikit-learn all about and why is it so important from the point of view of machine learning. We'll also see how to install it properly and get going. First things first, let's see briefly what machine learning actually is. Without going into formal textbook definition, in very simple terms, one can say that if performance of doing a particular task is improving with experience, then we can say that the machine or the model is learning. So there would be some task and we'll see how good the task is being done. And this is done by measuring the performance. If we see that the performance is increasing and getting better with experience, then we can say that our program or our machine is learning. Mainly there are three types of machine learning, or we can say that all machine learning algorithms basically fall under these three categories. First one is supervised learning, second unsupervised learning, and the third one be reinforcement learning. In case of supervised learning, the correct label or answer is provided with data. As a classical example, size of houses are given with prices. After feeding this data, the program will learn and build up a hypothesis or model, and then we will give a new size, and the model will predict how much price should be based on the training data. That is the data we fed earlier. In supervised learning, no labels are provided. Instead, based on the similarity in data, it creates groups by itself. If you have visited Google News before, then you must have noticed that a particular piece of news covered by several websites are grouped under one section. These are not just grouped, these are rather clustered in one section. This can be one example of unsupervised learning. In case of reinforcement learning, there is an agent and he has to fulfill an objective or a reward. This objective can be winning a game or beating an opponent. So the agent has to decide which step it needs to take or which option it needs to be selected out of the various available options. Based on the choice, he gets either an award or a penalty. Also, selecting a choice opens up new possibilities. So you have to choose one state out of the many states available, and this choice has to be made while keeping in view that the reward is to be maximized. If you Google about the most popular programming languages for machine learning and data science, you'll find out that Python tops the list. And it would be great to know that Scikit-Learn is one of the most popular libraries to implement machine learning algorithms. It is easy, it is clean, and has a lot of efficient tools and features for classification, regression, clustering, and so on. It is built on NumPy, SciPy, and JobLib, but it is also recommended to install Matplotlib with it because Matplotlib is an excellent plotting library and makes the data visualizations very easy. Let's move ahead to Python and see how to install the scikit-learn library. We are assuming that you have installed the latest version of Python and set path and all the other variables correctly. Now let's type import Sklearn. As you can see, an error has been shown by Python that the module has not been found. That means it has not been installed yet. So let's head over to the command prompt and install it using the pip command. I opened command prompt and here goes our first command. So we have to install some libraries which are NumPy, SciPy, JobLib and Matplotlib. To install them, we will type pip install NumPy. As we have pressed enter, you can see the process has begun and it will be installed in a very short period of time. In a similar fashion, we will write pip install followed by the name of the library which we wish to install. For example, SciPy or Matplotlib or JobLib or Sklearn. After pressing the enter key, the library will get installed and after that we can import it in Python and use it accordingly. There are some queries and suggestions from the previous video for which we are extremely thankful, and they are to be addressed. So the first one is that this diagram is just used to bring the three keywords in one frame and hasn't really got much to do with the union, intersection, complement, or any of those operations of Venn diagram. A machine is said to learn if its performance of doing a certain task increases with experience. Also, while it's 100% correct that there are three main types of machine learning, many algorithms don't strictly fall under only one category. There are many algorithms, for example, say recommender system, that may see parts of supervised and unsupervised and come up with an optimum solution. Now that you have installed scikit-learn and the other required libraries, let's dive forward. Before we begin to tune or build our model, we'll obviously first need to load the data to begin our work in the very first place, right? Also, on a short note, we don't use all the data available to train our model. We reserve some part of it for testing our model. Now, why can't we use same set of data for training and testing? Simple. Because the model would already know the correct label for those instances. It is like getting same sum in exercise as it was given in solve problem section example before, or getting the exact same question in test which your teacher taught a day before. I hope you get the picture. We'll discuss more about splitting our data in training and testing set later, but first let's get clear with loading the data first. The library itself comes with a few small datasets which are known as toy datasets, and they are mostly used for seeing the manner in which classification and regression algorithms are being implemented. Here is a list of all the standard toy datasets mentioned in the documentation of this library. Since they are pre-built, no downloading is required, and we can load them as follows. First of all, we'll import scikit-learn. Now, from scikit-learn, we will import datasets. If you are interested in viewing the complete list, you can always write dir, and in the bracket, you'll have to write datasets. Okay, so the complete list has been loaded, but we are only interested in loading the toy datasets. So let's just name a variable, say iris, and we'll write datasets dot load iris. So now iris contains the iris dataset, and we want to know that how many samples are there, what kind of features are there, how many features are there. So let's start exploring this. We can write print iris dot. After that we can write okay, the list has been popped up. We can use data, feature names, file names. If we use the feature names, then it will actually show that what are the column headings. So let's write feature names. So you can see that there are four columns. First one containing sepal length in centimeters, second one containing sepal width in centimeter, third one containing petal length, and fourth one containing petal width. So there are four columns. Let's see what's the data. Print iris dot data. So you can see it has been written that squeeze text 150 lines. So means that there are 150 examples. Let's double click on this to expand this. Okay, so as you can see, as we had seen earlier, there were four columns, and accordingly four columns have been shown and 150 examples are there. So now we know that there are 150 flowers whose sepal width and length and petal width and length have been recorded. Now let us see what are the target values and under what name are they saved. So we'll again write print iris dot target. 0, 1 and 2 are the values in which they are mapped. So first 50. So there are three kinds of flowers. That's why we have three values under the target section, and let us see their names. Print iris dot target underscore names. Okay, something's wrong. I messed up the syntax a bit. Print iris dot target names. Okay, yes. So the three values which had been mapped to 0, 1 and 2 are actually the flowers setosa, versicolor and virginica. For more details about this dataset, you can always write print iris dot followed by DESCR all in caps. DESCR. This will give you a description about this dataset. Okay, let's double click to expand this quiz text. Yeah. So as you can see, everything has been specified over here. For example, number of instances are 150, 50 in each three classes. Number of attributes are 4, which we had already seen earlier. And these attribute informations are sepal length, sepal width, and etc. The classes are also specified over here. So in the DESCR attribute, you can also find who's the author, at what time was this data set released, and other specific details. Like we used load iris a few moments ago, you can similarly load any data by typing, for example, load underscore digits or whichever you wish in the same way. Other than the toy datasets, the other set of real world datasets can be fetched and downloaded if necessary. These are the list of datasets that can be loaded using the fetch command. Again, this complete list has been taken from the documentation itself. OpenML.org is also a very popular public repository for machine learning data. Here's how we can download a dataset from there. Suppose we want to download this dataset of mice protein levels, which are helpful in studying associative learning. So just search mice protein. Press the enter key. Yeah. And this result which pops up. Here all the description about this dataset can be found, and we have to download this dataset only using Scikit-Learn. So we import Sklearn, and from Sklearn we import our datasets, and after that from sklearn dot datasets we import fetch open ml. After this we need to give a name to a variable, and we'll write fetch underscore open ml, and here we need to specify two things about the file. Name is equal to mice protein and separated by version equals to 4. Mice has been loaded, and we can see the details as follows. So that is how you can download any data set from the openml.org repository. We can also generate our own datasets in Scikit-Learn using the commands which begin with make, that is make underscore. For example, make underscore classifications or make underscore regression. But we are skipping this for now, as we believe that it is relatively less important from beginner's point of view as compared to other discussed methods previously. Depending on the data and its format, we can use different libraries for it. For example, if your data is of the SQL, JSON, Excel or CSV file, then it is best to use Pandas library for it. Pandas comes with read CSV, read Excel, read JSON and read SQL commands, which make it very easy and convenient if you have files in these formats. Also, the data frames can be created of dictionary type object using lists and tuples. But if your file is of a binary format, for example, if it has extension of .mat or .arff or .wav, then it is recommended to use SciPy library. And if there is columnar data, then NumPy array should always be preferred. And as far as the image and video are concerned, then we can load them to a NumPy array using the skimage library. All these libraries interoperate very well with the scikit-learn, and I'll leave the links related to these libraries in the description below. So by this point of time, we think that we have covered all the majorly used data forms and how to load the data in scikit-learn using them. Still, if you think that there is a data form or any method which is missed and has not been covered yet, then do mention it in the comments below, and we'll try to cover it up. We are now in a position to take a step forward and to build a model, and that is exactly what we are going to do in this video. We'll be downloading a dataset from Kaggle and build a classification model, and finally we'll see how good a model is doing at predicting or classifying. Now let's proceed to have a look at the dataset on which we are going to work. So open Kaggle and search for seed from UCI, and you will land up on this page. Let me zoom it so that it is more clearly visible. Yeah. So the file is of just 9 KB and it gets downloaded in a Ziffy. I've already downloaded it. Uh, it contains 3 varieties of wheat. Yes, it contains 3 varieties of wheat: Kema, Rosa and Canadian, 70 elements each. So that gives us a total of 210 elements. It has 7 data columns describing each instance or example. And finally, there's a target variable, which is the kind of wheat, and that is what is to be predicted. These are the column headings or the data which describe each instance of a particular wheat. After downloading the file, if you open it through Excel, this is how it will look. As you can see, there are a total of 8 columns, 7 data columns, and finally a target column. And there are a total of 211 rows, and the first one was for heading. So this gives us a total of 210 rows and 8 columns. Now let's head over to Python and get the real work started. First of all, we'll import pandas as PD following the convention. We will now name a variable, say total data, and read the contents of that file in this variable. This will be done using the pd.read_csv command. And if the file is present in the path, then you can directly write the name of the file. But in case the file is present at some other location, you can write r followed by the path of the variable. We can reconfirm about the details of the data by using describe command, that is total_data dot describe. So as we had seen in that Kaggle dataset page itself, there are exactly 210 rows indexed from 0 to 209, and there are 8 columns as expected. So after this, we will take all the data variables in variable say x, leaving aside the target variables. So we'll write x equals to total_data, and then we can use a lock method and use the column names or just drop the last column. But I prefer the ilock method because of its clear-cut indexing. So we'll write total_data dot ilock, and then we'll put the square brackets. Then I want all the rows, and then the column number 0 to 7th. And if you are familiar with this indexing, then you know that by doing this, we are not including the last column. And again, we can get reconfirmed about this selection by typing x.info. You can see the last column, that is the column of target variables, has been dropped, and we are left with 210 rows and 7 columns as we had expected. In a similar fashion, we'll use a variable say y to store all the target variables. Again, we'll type total underscore data, and we'll use the ilog method, put the square brackets. I want all the rows but only the last column. Again, we can check out all the details by typing y dot describe. So yeah, 210 rows. We will now import Scikit-Learn and other required libraries for this project. Import Sklearn. From Sklearn, import SVM, that is support vector machine. And from sklearn.svm, let's import SVC, that is the support vector classifier. Okay, looks like I messed up the syntax a bit. It will be capital SVC. Yeah, it's good. Before we move ahead and work on the support vector classifier, let's discuss a few terms about it and have a look about what it actually does. So SVC is a classifier, and it's of course supervised because we have to supply labeled training data. What it does is that it comes with the best or optimal separating boundary or hyperplane, which classifies new unseen examples. The different kinds or categories of data are separated by a clear gap as wide as possible. There are a number of parameters that can be tuned if required, and we'll discuss them too once we train our model later in this video itself. However, for simple data sets like the one we're going to use, the default settings work out to be just fine. As we have already explained about train and test data in previous videos, we'll just partition the current dataset into the ratio specified by us. So from sklearn dot model selection, will import train test split. Train test split. If no value is supplied, the default ratio is 3:1, that is 75% of data for training and 25% for testing. Also, it's not like the first 25% instances will be used for testing or last 25. The examples are selected randomly. So we'll name some variables such as x train, x test, y train, and y test. Then we'll write train test split. And then we'll specify the data, which is x, then our target variable, that is y, and after that we can write test size equals to 0.2. That means 20% of the total data will be used as testing set. If nothing is specified, then as we had said previously, 0.25 is selected by default. And we can specify one more variable, that is one more parameter actually, that is random state. And we can give any number because this is actually just a random number generator, and the number provided over here will be used to seed the values. So let's say 13. Now we will import standard scalar. So we'll write from sklearn dot preprocessing, import standard scalar. It is always a good practice to scale the data. If you would have paid attention, there were some data which were 0 point something and some were near around 15, 16 or so on. In other data sets, this difference may be even bigger. So what happens is that there's a huge chance that the bigger number will outweigh these parameters, and the smaller number won't be contributing much. So to bring them on a relatively same scale where the difference isn't much pronounced, we scale it and provide a level playing field. The gradient descent also takes a lot of time to converge at a minimum because the contours are skewed if not scaled. But okay, if you start discussing about that, this video will become too lengthy. Do let us know if you want to cover, if you want gradient descent to be covered in the next video. But for now, let's focus on the implementation. So we'll now write SC equals to standard scalar followed by a couple of brackets. After that, we'll write xtrain is equal to sc dot fit transform xtrain and xtest as just sc dot transform of xtest. Now you must be wondering that why we are using fit transform method in case of train and just the transform method in case of test. So the thing is that we can use both the fit and transform method one after the other, or we can club it together as we have done in the training set. So when we scale the data, we actually apply the mean normalization. So the two parameters that are learned while scaling the training data, the same parameters are used to scale the test data, and hence no fit method is used in case of test data. So let's proceed. Now let's name a variable and call our classifier. After calling the classifier, we will now pass the training data in it. That is, we will write clf dot fit. After that, we'll write x underscore train comma y underscore train. There are a lot of parameters, but we'll discuss about the most important ones. So C is the penalty parameter. If C is less, decision boundaries will be smooth, which is desirable, but accuracy won't be that high. If C is more, then overfitting may occur, but accuracy increases. So there's a trade-off. Again, we have different algorithms regarding this too, but for now, let's stick to default values. Kernel is RBF. RBF stands for radial basis function, and it has infinite number of dimensions. It can have infinite number of dimensions, and its value decreases as we move away from the center. Finally, we have gamma, which is a parameter for non-linear hyperplane, and the higher the value of gamma, the higher it tries to fit the training data more exactly. We are now left with the job of predicting using our classifier. So we'll name a variable, say pred underscore clf, and we'll call the predict function clf dot predict, and we'll pass x underscore test to it. But wait, our job is not finished here. We need to see how accurate our model is. So we'll write sklearn dot metrics dot accuracy underscore, and we'll pass y underscore test, that is the what it should have been, and pred underscore clf, that is what has been predicted. So its accuracy level is more than 95%, and hence we can say that our SVM classifier is doing a pretty good job in predicting. If you want to dig further deeper, you can also generate a classification report. For that, you'll have to write sklearn dot metrics dot classification report, and again what it should have been, y underscore test, and what is predicted, pred underscore clf. It was not very readable, so I used the print command, and now you can see that it has all been beautifully formatted in our table format here. Precision is the ability of classifier not to label an instance positive that is actually negative. It is accuracy of positive predictions. And recall is ability of classifier to find all positive instances. It is a fraction of positives that were correctly identified. And F1 score is a harmonic mean of precision and recall. So finally we made a model whose accuracy was more than 95%, and there were quite a few new terms, methods and concepts in this video. If you want to know about any particular topic in detail, or you are unclear about any of the process shown over here, then make sure to leave it as a comment below and we'll try to take it up in the next video. Thank you for your time. This is Abhishek Singh from Programming Knowledge, and check out other videos and subscribe to the channel for more such content. Thank you. In this video, we'll learn about the concept of pipeline. Now, a typical pipeline consists of a pre-processing step that transforms or imputes the data and a final predictor that predicts target values. So transformers and estimators, that is the predictors, can be combined together into a single unifying object, that is a pipeline. So pipeline is combining different transformers and estimators to automate machine learning workflows, as it sequentially applies a list of transforms and a final estimator. Now that we have some theoretical idea about pipelining, let's head over to Python and code its simple implementation and see how it is actually done. So first of all, we'll import the required packages and datasets. So let's first import the iris dataset from sklearn dot datasets import load iris. Uh, we had used a standard scaler the last time, so this time let's try the minmaxkiller. We'll discuss about it in a while, but first let's import the minmaxkiller first. From sklearn dot pre-processing import minmax scalar. Now we'll import a simple linear model logistic regression. So from sklearn dot linear underscore model import logistic regression. And for splitting the data into training and testing set, the model selection is accordingly imported. From sklearn dot model selection import train test split. And finally we'll import the pipeline. So from sklearn dot pipeline we will import pipeline. Mind you, it is case sensitive, so be alert and use a capital P later and a small p before. Most of the things that we have imported, we have discussed about it in the previous videos. So I'm not going to detail into all of these, and in case you have missed any of those concepts, then do see our previous videos in this series. And still, if you are having any confusion, then do comment it as a comment below. Here, x is an element of a particular instance. So what minmaxkiller does is that it first subtracts the minimum of x's from x and divides the result by the difference of x's max and min. This intermediate result is now multiplied to the range, that is max and max minus min, and then the min is added. Min and max are nothing but feature ranges. Now let's write iris. Iris are a variable in which we will load our iris dataset. Iris equals to load iris. After that, we'll split our dataset into training and test set. So x underscore train, comma x underscore test, comma y underscore train and y underscore test. Let's call train test split method. In this we'll write iris dot data for x train, then iris dot target. These are for x and y respectively, and then we'll specify that how much percentage of the whole data set we want to be as our testing set. So let's say 0.2, that is the 20%, means 20% of our data will be used for testing. And let's seed a random variable, so random state, let's say 42. Now we'll create the pipeline, again a variable pipe underscore lr for logistic regression. Pipeline, mind you here P is capital. Again a variable's name minmax for minmaxkiller. After this, now that the scalar has been added, let's add our is the logistic regression estimator or predictor. Logistic regression. Okay, now let's fit our data in this pipeline. So pipe underscore lr dot fit x train and y train, x train comma y train. Okay, now let's see the score name. Now let's name a variable score and store the score in it. So right, pipe underscore lr dot score. Let's see how good our model is doing. X underscore test comma y underscore test. So as you can see, our model is 90% accurate in guessing the unknown examples or the examples that it has not seen before, and hence we have created a simple pipeline in which we have first scaled the data using the minmaxkiller and then applied a simple linear logistic regression for classifying the iris dataset. For any machine learning model, there are some hyperparameters which can be adjusted, and in turn they change the efficiency or the accuracy of the model. So even if we finalize the machine learning model that we are going to work with, a lot of job is still left as we have to adjust the hyperparameters. One brute force approach would be to start with default values and keep on adjusting manually according to our intuition, but that would be very time consuming and does not have any clear cut indication about whether we have reached an optimum value or not. That's where grid search comes in to make our life a little bit easier. We have already worked with the SVC and logistic regression. So instead of repeating them again, let's learn something new. In this video, first we'll learn about a new efficient classifier, that is a random forest classifier, and then we'll use grid search to tune its hyperparameters. For understanding random forest classifier, let us take this interesting example. Suppose you want to visit any one of the following cities, which are Delhi, Mumbai, Kolkata, and Chennai, but you are not sure which one. So you make a list of these four cities and distribute to your 100 friends and ask them to choose their favorite one out of these four. Some choose Delhi, some choose Mumbai, but after the voting, you found out that Kolkata has got the maximum number of votes. So now you can be sure that you want to go to Kolkata. That is how a random forest classifier works. A random forest is a meta estimator that fits a number of decision trees on various subsamples of dataset and uses average to improve predictive accuracy. Drawing similarities, we can say that these hundreds friends were like 100 decision trees, and each one of them predicted a value, and the final outcome was decided by a majority of voting, that is the forest. Let's see how it is implemented in Python. So as usual, first of all, we'll import scikit-learn. After, from scikit-learn dot ensemble, we will import random forest classifier. Then from sklearn, from sklearn dot datasets, we will import our iris dataset. That is by invoking load iris. Let's name a variable and load our iris data into it. Now we have to split our data set into training and testing set. So for that we'll import s from sklearn dot model selection, import train test split. Now let's split our data. We'll write x train, we'll write x test, then we'll write y train, then we'll write y test. Now let's call this function train test split, and in it we'll write iris dot data, then iris dot target. Let's specify the test size, say 20%, and seed a random value, random state equals to say 30. Now let's call our classifier clf equals to random forest classifier. It can be called in this way also. If we do not specify everything, then only the default values will be supplied. But for the purpose of this video, we are going to work with three very basic hyperparameters, which are number of estimators, minimum sample split, and minimum sample sleeve. So the default value for number of estimators is 10, that is 10 decision trees are used. Let's suppose we are going to work with just 2, number of estimators 2, and after that we can use min sample split. Min samples split equals to 3. The default value for this is 2, and min sample split is the minimum number of samples required to split an internal node. So of course its default value is 2. And the third parameter that we're going to work with is minimum samples leaf. Now what is minimum samples leaf? It is the minimum number of samples required at the base, that is at the leaf node. So its default value is 1. At least one sample is required over there. So let's try 2. Now let's fit our data into this classifier, clf.fit x train comma y train. Okay, the hyperparameters are as we had specified them. As you can see that minimum samples is 2, minimum sample leaf is 2, minimum sample split is 3, the number of estimators are 2. So yeah, let's go ahead. After fitting this, we are left with the job of predicting. Let's use pred underscore clf equals to clf dot predict, and what we are going to predict, x test. Now for checking the accuracy, we'll write Sklearn dot metrics dot accuracy score, and in the brackets we'll write y underscore test and pred underscore clf. Let's see how much accurate our model is with these hyperparameters. Okay, it's already 93% accurate. So now we'll see that can we improve this accuracy or not. So in order to improve the accuracy, we'll try to adjust or tune the hyperparameters using grid search. So first of all, let's import grid search from sklearn dot model selection import grid search CV. After that, we have to specify a parameter grid. What this parameter grid contains is it contains a various number of features, and we have to specify them according to our wish. So what it will do is that it will take each one of the combination and try it out. So in our case, since we have chosen to work with these 3 features, so first of all we'll specify n estimators. Now what are the values that we can work that it can take? So we had taken 3 initially, so 2, sorry. So let's say 2, 5, 10, 20. Suppose that my number of estimators can take any one of these 4 values. After that, I can write my next feature, that is min samples split, and this will be, it was given 3, so let's say 2 and 3. After that, which one feature is left? Min samples leaf. Min samples leaf, and min samples leaf can take up any of the values, like its default value was 1, so let's try 1, 2 and 3. So basically what we have done is we have given it 4 options for number of estimators, 2 options for minimum sample split and 3 options for minimum sample leaf. So a total of 4 into 2 into 3, that is 24 options it is going to try on our model, and the one with the best accuracy score will get selected. And that is how grid search works. So that is, number of estimators can take up any of these 4 values, 2, 5, 10 or 20. Minimum sample split can take any of these 2 values, that is 2 or 3, and minimum sample leaf can take similarly any of these 3 values, which are 1, 2 and 3. Now let's write grid search, and in it we will first call grid search CV, then specify our estimator. Our estimator was CLF, which is the random forest classifier, of course, and after that we have to specify the parameter grid. So both have been saved by the same name, I think. So yeah, param grid it will be. After that, after this we have to fit the data in our grid. So grid underscore search dot fit, grid underscore search dot fit xtrain and ytrain, xtrain ytrain. There's some kind of warning. Okay, we'll ignore the warning. And now that our grid search has done its working, so we'll see what are the best parameters that it has come up with. Grid search dot best underscore params, that is parameters. So the grid search has told us that minimum samples leaf should be 1, minimum sample split should be 2, and the number of estimators should be 5 for the optimum solution. So let's tune our random forest classifier, that is our model, according to these hyperparameters, and then check our accuracy. Till this point, the code is exactly the same as we had seen a few moments ago. So from this point, we'll specify the hyperparameters that we have learned using the grid search. So number of estimators were 5, min samples leaf was 1, and min samples split was 2. Now we just have to fit our data. clf.fit x train and then y train, y underscore train. Okay, the data has been fed. Now let's do the prediction. Pred underscore clf equals to clf dot predict, and after that we'll write x underscore test. The prediction has been done. Now the last step, that is we're going to check its accuracy. Sklearn dot metrics dot accuracy underscore score, and whose accuracy we have to check, y underscore test as compared to pred underscore clf. Okay, so as you can see, the accuracy has gone to 100%. This might be a case of overfitting, but one thing is for sure, that we tuned our hyperparameters using grid search, and then using those hyperparameters, the accuracy of our model definitely improved.